Okay, so we're continuing this morning's session with two short talks. And the first one is by Jack Farell, who's doing his PhD with Lucas, again, the University of Boulder, Colorado. That's right.
Yeah, okay. Apologies for not mingling. I was frantically finishing the slideshow. But I guess the main thing I want to cover today, I think I will try to fulfill some of the promises that my advisor has made in the first talk of this morning regarding how can one use some of these long wavelength hydrodynamic kinetic models or otherwise to answer questions you may have if you're given some chunk of a quantum material. You're trying to understand what kind of physics is going on. So I'll get into that, but let me first acknowledge my collaborators. So of course I've worked with Andy at Boulder and two strong students of Andrea Young and the PI there at University of Colorado, University of California, Santa Barbara as well. So to get into it, let's try to remember from the previous talk this morning that various properties of transport, including current flow patterns, can be extremely sensitive to like the strength of various types of physics that are happening in a device, and also on the type of physics that is happening. In particular, we might sort of roughly try to categorize these into different regimes. So one regime that we could talk about could be called ohmic or diffusive, and this would be parameterized maybe by some number called gamma momentum relaxing. So now the rate at which momentum of electrons is being lost in a system. And a trajectory, if you do have a quasi-particle, would look just like random walk, diffusive random walk in this picture. On the other hand, it's also been introduced this hydrodynamic regime where now we introduce another timescale, gamma momentum conserving. And if that is much faster than this momentum relaxing scattering rate, then we're in this hydrodynamic window, and we may hope to see viscous transport of electrons. And in some sense, the simplest one would be where both of these numbers are close to zero. And this we would just call ballistic flow. Trajectories here would be, semi-classical caustics, and electrons are basically just scattering only from the boundaries. But we have these three rough regimes, and real materials or experiments are often operating in crossovers or intermediate windows between these regimes. So the question I'm going to try to answer in today's talk is, how does one actually use various transport observables, space-resolved or otherwise, to determine these parameters? And it would be best if we can try to determine these parameters quantitatively to some degree, although you'll see the kind of cartoonish models that we're still using. In particular, these space-resolved imaging experiments are extremely powerful, but it does feel a little bit like overkill if you're trying to only determine order one numbers from some experiment, and you have to do a full space-resolved map, which has somehow infinite degrees of freedom. So I'm going to try to give you an alternative way to do this. And it comes down essentially to old idea from field effect transistor, like semiconductor physics, about looking at different branching ratios of current through different drains in a device. And in particular, the device that I've come up with, although I'm not claiming it's optimal or the only device that would have this property, it looks like this. So you have one source down at the bottom that I'll call south, because at like the bottom of the compass. And then you have four drains. So you have a north one, northeast, east, and southeast. And you want to think about the amount of current that's going to go into all of these drains. And all the drains, you try to your best to hold them at the same potential, which we might call ground in this experiment. And of the source, you would hold that at a slightly higher potential. So let me try to give you some design principles of why we might expect this device could help us distinguish these regimes of transport and tell us something about the scattering processes or physics that's happening in the device. Let me start with the ballistic case versus these hydrodynamic or diffusive sort of together. And that one, a pretty simple principle that ballistic charge carriers, if they're moving in semi-classical trajectories, they should just want to go in straight lines. So you should expect that the majority of the current simply goes up into the north drain if it's injected by the south source. But the slightly more difficult one is to try to distinguish hydrodynamic case from the diffusive case. And in order to do that, I'll explain why this device should do this as well. But to do that, we have to remember some expectations for this diffusive and hydrodynamic regime that were covered in the previous talk. In particular, if you have a rectangle, and notice that all of these drains at various angles are just rectangles, and it has some length and width, then for the diffusive case, or this ohmic case where there's momentum relaxation, we expect that the total resistance of this rectangle should simply be proportional to the length over width of the device. Whereas for the hydrodynamic case, due to this channel, Poisson flow, we instead, there's a typo here. We should have 1 over width to the power of 3, 1 over width to the power of 3, rather than just repeating the same thing previously. And so it's unfortunate that the key point is missing from the slide, but there's a much more sensitivity to the width of the device for the hydrodynamic case. So the idea, when I drew this geometry in Inkscape, the idea was to create channels that actually have a fixed length over width. So from an ohmic perspective, all of these channels are sort of the same, but you'll see that they have slightly different lengths and widths. So they should be, any difference in resistance through these drains that you see should be attributable to hydrodynamic flow rather than diffusive. So it should be able to distinguish all 3 regimes in some way. But okay, how are we going to sort of quantitatively calculate which fraction of current should go through the various drains of this device, given some boundary conditions? Well, I can answer that question. And to do that, we're going to work with a pretty cartoonish kinetic theory for electrons moving through this device. In particular, it's just a linear Boltzmann transport type of equation. So we're dealing with a bunch of electrons with a circular Fermi surface, so some energy dispersion that depends only on the magnitude of the momentum. And the Fermi surface will just look like a circle, and we can think about a momentum on this Fermi surface just in terms of an angle. And in particular, we'll think about the single particle distribution function, so roughly how many particles, or the probability of finding a particle at a certain position and momentum, and you could think of time as well. And we'll take equilibrium to be close to 0, so it's just a Fermi-Dirac distribution, which is a step function, so you have a particle inside the Fermi surface and nothing outside. And in that case, one could write down a sort of semi-classical equation of motion for this distribution function, which is a Boltzmann equation. So on left-hand side is sort of what you would have in the ballistic case, where you can think that free particles are just moving in semi-classical trajectories. And the right-hand side, all the interacting physics, that is electrons interacting with each other or with their environment, is in this term C, which I'll refer to as the collision integral or collision term in various cases. And then if we want to do linear response, we can parameterize the deviation from this equilibrium just conveniently in terms of this distribution function variable called phi. And the reason for this is that all the non-analyticities of this step function are sort of absorbed in that variable. And then we need to instead write down a transport equation for this phi linear response deformation of Fermi surface instead. And I'll also relabel the collisions, I'll call it W when I'm talking about this phi instead of C, just so I don't get confused. And a convenient way to try to solve this equation is actually to expand this phi variable in terms of Fourier harmonics. So one can make an expansion that looks like this in 2 dimensions. And the reason for that is that the low order harmonics are related to the various conserved quantities. So for example, the monopole in blue is related to the very non-equilibrium charge density, and the dipole, so it would be A1 or B1 coefficients of this Fourier series, are related to the momentum density as well. So it's kind of like the conserved quantities are well encoded at the very low part of this distribution of this Fourier expansion. And in this case, what we find is that the Boltzmann equation for phi, or for F, if you like, it becomes like an infinite tower of coupled partial differential equations for these Fourier harmonics. So I'll write out a couple of them and then I'll give up. So for the first one, you can think for the A0 monopole harmonic, it's kind of like the continuity equation, just saying charge is conserved. And then for the one harmonic, so this is like the equation of motion for momentum density. So you can think it's kind of like the Navier-Stokes equation. And here we want to say that momentum can relax. So I'll give it this phenomenological relaxation rate, gamma momentum relaxing. And then for all higher harmonics, at least at this part of the talk, I'll say that these ones can relax at a higher rate, which is actually the momentum relaxing rate plus momentum conserving rate. And those were defined like roughly at the beginning of the talk in terms of these scattering mechanisms that we expect to be present in these different regimes. But there's
the right hand side comes from the Boltzmann equation, or is something that you put by hand?
No, it's phenomenological collision. So one could think of this as a two-rate relaxation time approximation to the collision integral. And there's much more interesting things happening for electron-electron scattering in 2 dimensions at low temperature, but one's welcome to consider those or not. But it's phenomenological. Any other questions before I move on?
A1 in the bottom right or AN?
AN. Good question. So another typo, AN appears on the bottom right. Okay, any more questions?
So then how is it gamma MR on the bottom right?
I guess you could
Because you want to take a moment, right, of that equation to isolate momentum. And
no, I think I
isolate
prefer to think of gamma MR as relaxing momentum and everything higher than momentum. So if you think of like old school Ashcroft-Mermin relaxation time, it would be like the whole distribution function relaxes at some rate gamma. So gamma MR relaxes momentum and every harmonic higher than momentum. And gamma momentum conserving relaxes, let's see, everything higher than momentum only. I think it's a more convenient parameterization.
Maybe just another way to say it is like in this parameterization, gamma MR and gamma MC could each sort of be anything between 0 and infinity. But if you sort of called the thing in the bottom right just gamma MC, then somehow it might be nonsensical to have gamma MR larger than gamma MC.
That's right.
So it just changes the like parameter space you should explore. It's just, I think it's better labeling choice.
Question?
Oh, I was just comment that if the collision operator for electron-electron scattering just has momentum conserving terms in it, so we don't have a lattice here, then the gamma MR here would just be a diagonal collision operator that's added on to the electron-electron component. So then this rate would be the sort of total eigenvalue that you get for the combined operator, which is why it would be a shift in all the rates. So I think that's one way to look at it.
Yeah, maybe I should have spent more time correcting the typos rather than making pictures in ChatGPT. Okay, I'll move on then. Okay, so once one has this infinite tower of coupled partial differential equations, the next trick is just essentially to solve them directly in real space using a finite volume type of method. So I'm going to directly like time step until it reaches steady state, this giant set of PDEs, but of course I have to truncate it at some maximum harmonic. And the benefit of this sort of Fourier method is that one can get away with pretty high truncation in hydrodynamic limit because the conserved quantities are captured in the low order modes. So there's a benefit to the spectral approach. So I'll articulate that method right now. So here's the geometry from one of the experiments that Andy has mentioned in the previous talk. So there was like a source and a drain. And then there's some algorithms you can use to basically like find simplices that cover this domain. So you just need to discretize into some quadrilateral mesh. And then there's a black box that I found implemented in Julia programming language that goes by name of high order discontinuous Galerkin spectral element methods. So the idea is that this continuum PDE in space can be, the solution to it on each of these quadrilaterals can be represented as a high order polynomial. So I've used a fourth order polynomial in each of these quadrilaterals, and then you try your best to like match between them using finite volume type of fluxes, but this would be a good thing to cover offline. And then, okay, so once you do this with various choices of boundary conditions, various choices of these phenomenological scattering rates, you can make a map of the space-resolved currents magnitude. So that's what's being shown in the color bar. And you can make like streamlines to try to look at vorticity and things like this. So this was how we were able in a previous experiment to quantitatively estimate with space result imaging these phenomenological relaxation time type of parameters. In particular, we've studied wall boundary conditions of various kinds, including like you can think that the particles, when they hit a wall, they're re-emitted at a random direction. That would be like a dirty wall microscopically. Or you can think that the wall is like a mirror. So the particles, when they hit it, they just bounce off, and angle of incidence equals angle of reflection. That would be specular. Or you can try your best to blend them in some phenomenological way. And okay, you're welcome to try to use this or modify and improve it, and let me know if there are errors. I put it up online for you to do that, and the reference for the experiment is here. And now let's return to this geometry that I had introduced previously. So okay, I'll remind you of this slide, and again, note the error, please. So this is the geometry that we're thinking about, in particular north, northeast, east, and southeast are the important sort of drains to have in mind for the previous slide, for the next slide, I should say. Okay, and let's try to take a look at the ballistic hydrodynamic diffusive crossover that we can try to model in this device. So what am I showing you here in these three heat maps? Well, for each one, the X and Y axis are the two scattering parameters that we have. So on the X axis, I have the momentum conserving one, which you could think of like electron-electron collisions. And on the Y axis, I have the momentum relaxing one, which you could think of as interactions with like maybe phonons or with impurities in the crystal lattice. And what the heat map is telling you is various currents, various fractions of currents going through the drains. And I've always normalized to the north contact. So that's the one that we expect to be biggest in the ballistic case. So I'm showing you the northeast current divided by the north on the left. In the middle is the east divided by the north. And on the right is the southeast divided by the north. And okay, what are we supposed to get from looking at these images? Well, in each one, but especially in the northeast contact, it's sort of biggest in the ballistic regime, which is the bottom left-hand corner. And then, there's some seemingly non-degenerate dependence on the scattering rates between these fractions. But it's just numerics at this point, so I'm not sure how much there is to say. But I guess the question I was sort of interested in is, if I were like handed these three heat maps, and I was also given a precise measurement of the three fractions in an experiment, could I infer this momentum relaxing rate and this momentum conserving rate in some sort of best fit or Galerkin type of way, just from the single measurement of the three branching fractions? It should be simple to do, although I'm not sure how this current could be measured, but I have various ideas. And okay, and I'm not fully sure of the best way to answer that question, like to talk about how hard that inverse problem is and how well posed it is. But okay, one thing that you could try is to think about the map between the momentum relaxing rate and momentum conserving rate to these three current fractions. Think about the Jacobian of that map and look at the singular values. That would tell you something about the worst local sensitivity that you could have to one of those two parameters. And indeed, you have three observables, and you are only trying to estimate 2 rates in this picture. So it should be doable. Just one sec. And what we found, if we plot the lowest singular value of this Jacobian, is that in the crossover regime, you should have pretty good sensitivity to these 2 parameters, and it should be possible to solve the inverse problem. But it would be interesting to try and with some real experimental data where there's noise to see what those error bars look like. I will say in the ohmic regime, which is at the top, it becomes not well posed anymore. But that makes sense if your scattering rates are like let me see, if your interaction length is too long compared to the size of the device, you should sort of lose sensitivity to these numbers in the first place. So you need your geometry to be sort of tuned to the region of parameter space you're trying to infer. But there's a question.
The color map, it's which one is ballistic and which one it's diffusing?
Oh, sorry. The ballistic in all 3 of these pictures would be the bottom left corner of each picture, right? Where the scattering rates are all close to 0. And the hydrodynamic regime would be the rightmost part of each heat map, where momentum conserving scattering is faster, stronger than momentum relaxing scattering. And diffusive or ohmic would be the top part of each figure. So that would be where momentum relaxing scattering is dominating over momentum conserving physics. So the whole phase diagram is present for all 3 contacts.
So your model is based on the geometry, regardless the type of the system that you are using.
Yeah, so okay, let me just maybe take a step back. What I did was in this geometry, simulate that Boltzmann equation with these 2 types of momentum relaxing scattering. And I did that like 1,000 times at a bunch of different values of gamma MR and gamma MC. And then I put all of those gamma MR and gamma MC values into a heat map for this geometry. But I could do it for any geometry that you give me and any number of contacts. So if there's a better one, it would be definitely interesting to find. We just, we had some principle by which we thought this geometry would be sensitive to the things we were interested in. Good enough? Or nothing? Yeah, lots of trees were killed to create this slideshow. Should I move on? Oh, Marvin?
So, yeah, maybe I didn't understand how complicated this inverse problem is, but just based on what you said, right? Like, if you measure, these different fractions, could you not just do the reverse of what you said? Is like, which is, if you're on like the top rightmost part of this thing, then.
Yeah, qualitatively, it should be very straightforward to delineate which like regime you're in. But I think if you want to actually get a number,
I see.
For these 2 phenomenological parameters, that's the difficult part. But we have some argument that you should be able to do it. And then when I like tried playing this game, so I give myself a measured fraction, yeah, I do find there's only one answer. But the question would be noisy experimental data. Okay, let me, I only have a few minutes, but I want to say a couple of things about the more interesting structure that electron-electron collisions have in 2 dimensions. Namely, when we're on a Fermi surface and we're actually considering a 2-body scattering process between electrons, we need to be really careful about the kinematic constraints, namely that, first of all 4 momenta have to live on the Fermi surface. And we also need to conserve energy and conserve momentum in the scattering process. And what we find actually, if you think about this carefully, is that the largest phase space for this scattering process has to do with this nearly head-on collision, where the 2 electrons are just on opposite sides of the Fermi surface, 2 momenta that is. And then afterward, they're also just on opposite sides of the Fermi surface, and their angle hasn't changed very much. So this is the type of scattering that should dominate low temperature Fermi liquid electron-electron scattering. But the point is that this picture that I drew of this scattering process has an approximate inversion symmetry. So the collision integral approximately actually annihilates the inversion odd sector of this phi like angular Fermi surface deformation. So we could like approximate that the rate is 0 for any inversion odd component of this phi variable. but we'll still call gamma momentum conserving the relaxation rate of the even part. And then you can do even better. If you remember the Fourier expansion, we could try to give a different rate to each harmonic of the Fourier expansion. And it will be argued, perhaps in a previous talk today, or by various people, including Levitov, I think, that the odd rates should scale like with the harmonic number to the power of 4, and they're parameterized by this new number that's supposed to be purple called gamma 3. So I've introduced one more rate that now gives the relaxation rate roughly of the odd modes of the Fermi surface. Okay, and we can talk more because I have to be a little fast. But the point that I really want to make is that this geometry that I drew is also sensitive to these like mode resolved or more careful fine structure of the electron-electron collision integral, which you can calculate with Fermi-Golden rule. In particular, the expectation is that the electron-electron scattering length, which is the momentum conserving one, scales with temperature squared, while this odd, anomalous, like inversion odd relaxation rate scales only with temperature to the power of 4. That's why it's smaller at low temperature. So what we can do is imagine sweeping the temperature at various like ratios between these two and try to see how these fractions behave. So what I'm showing you in this picture here is some sort of phase space portrait. So I imagine a sweeping temperature would be like traveling along this curve. And I'm showing you the trajectory in the phase space of the northeast current fraction and the southeast current fraction. And indeed, you see something different. A sharp feature in the yellow curve appears in the case where the gamma 3 was sort of smaller at first than the gamma EE. Cusi would be like at m equals 3, how small is gamma 3 compared to gamma 2? I can also do this like sort of more generally, just sweeping the parameters numerically for this odd rate relaxation. And there should be a signature of this anomalous scaling. In particular, if you look at this northeast current fraction, it is smaller than 1 at low gamma 3, and then can become higher than 1 for high gamma 3. So it should be a clear qualitative signature that this fine structure of the collision integral is correct. But there's a question.
So what's the meaning of the color on the line?
For this one? Yeah, okay. So the color of the line is roughly, okay, so gamma EE is like T squared, right? And gamma 3 is like temperature to the power of 4, right? So I can think that gamma 3 is like gamma EE squared with some prefactor, and that prefactor is the color.
Okay, that's
so it's like the strength somehow of this odd even effect. So high Cusi is what I've labeled the color bar. High Cusi would be like very strong even odd inversion odd effect, and low Cusi would be that effect doesn't exist at all, which would be the simpler model from previously in the talk. Any other questions? Okay, and I should finish, so I will skip a few slides, but I do want to mention that we have some ideas about how to generalize to more complicated Fermi surface shapes. So instead of circular harmonics like Fourier series, one needs to come up with more general orthogonal functions. And I was just playing around with this on the airplane, but I think it can be done. So if you had a Fermi surface that looked like, that had this very delicious shape, then you can come up with what those orthogonal functions would look like and try to still make a similar spectral method. And what I hope to do in the future is to try to do these space resolved models in devices like the one that I sketched, or maybe in general, including the honest collision integral with anisotropic Fermi surfaces. In particular, it would be neat to see if you can engineer geometries in 2 or 3 dimensions to try to measure whatever parameter of your transport that you care about. It could be this rotational viscosity that Andy has previously advertised. And I expect that from the machine learning literature, like inverse design methods could help us sort of find optimal geometries. So if you give me some transport, some modeling parameter that you would like to distinguish using one of these like multi-terminal type of measurements, maybe I can run some algorithm and find you the optimal geometry to cut your graphene or whatever into in order to be most sensitive to that number. So that's the idea there. But okay, otherwise I'll just say thanks and maybe answer 1 or 2 questions before Davis takes over.
Davis, do you mind coming up and joining the Zoom so we can transition smoothly? So this time for one question while Davis is setting up.
So maybe our experimental colleagues could chime in, but we thought about this experiment, the one that you said with the 4 branches.
Yeah.
My experimental colleagues, they shot me down because the variation in the contact resistance is going to create so much noise that you cannot distinguish.
Yeah, I know.
About this?
I think that it would be okay if, like, could you imagine just all of those 4 drains are just connected to the same gold piece?
Yes, but then you can no longer distinguish the currents. So then you go back to the imaging to.
You need a different way to distinguish current. And then the question is, okay, if I'm doing that, might as well just do the imaging, which is more robust anyway, but maybe there's some way. I will say we thought about a different configuration as well, where instead of measuring the current fraction, you measure the non-local like potential at each of those drains, which is what is usually done in like a 4, what would it be, the 4 terminal transport measurements to avoid contact resistance, and the same effect appears. So that's in our appendix, but I like the current one. It's just simpler to explain. Finley? Thank you. Yeah.
Okay, thank Jack again.